In part C, we want to know what are the maximum and minimum values of the slope to the function negative sine of x. Okay, so let's intuitively do this first. Okay, the slope is flat. Okay, at these values, right? Okay, so let's start with this trough. Okay, as we move to the right, what happens to the slope of the tangent? It gets bigger, right? And looks like at that point, okay, the slope seems to be about that much. But after meeting this point, what happens to the slope? They sort of get smaller, eventually hitting a value of 0 or a flat slope, right? So it looks like the maximum slope is achieved at this particular point. And if we continue with the same intuition here, okay, we see that the slope gets smaller and smaller. Okay, and it's the steepest here, and it becomes less and less steep as we once again approach a slope of 0. Okay, so it looks like these points, this point and this point, are our points of interest. So how do we know exactly, okay, when this maximum slope occurs? Okay. Well, our initial function, negative sine of x, had a derivative of negative cos of x. Okay. And we want to know for what value of x is this going to be a maximum. Okay. So if you remember, back to optimization problems, okay, if you were given some function, say y is equal to x squared, and we wanted to know at what value, okay, I'm going to change this function and call it negative x squared. For what values of x is y a maximum? What do? We took the derivative, right? We took the derivative of our initial function and we set that to 0. Okay. And solving this equation, obviously here yields 0, and we know that the maximum or local maxima or minima occurs when x is equal to 0. And in fact it does, right? This is a inverse parabola, and its maximum point occurs when x is 0, and the maximum itself is also 0. Okay. So we're going to do the same thing here. We want to know for what values of x, okay, is negative cos of x a maximum. Okay, so to find out, we're going to differentiate our derivative. We saw that this is simply sine x is equal to 0, and we're going to set that to 0. So for what values is a function sine of x equal to 0? Okay, well, we know that, right? If we roughly sketch sine of x again, 0 occurs at pi, 2 pi, 3 pi, 4 pi, and so on and so forth. Okay. So solving for this, we get, pi, 2 pi, 3 pi, 4 pi, and so on and so forth. I'm also going to add 0 here, obviously. We have 0 because our sine of x extends to the negative side, right? Okay. So when x is equal to 0, okay, it looks like we have a local maxima or local minima. Okay, and looks like when x is equal to 0, obviously that point corresponds to the slope here. Okay, so let's plug 0 into our derivative, which would be negative cos of 0. And we all know that cos of 0 is equal to 1, so we get a slope of negative 1. Let's do the same thing for, say, pi here. Okay, pi looks like we have a positive slope, and that's our maximum slope there. So y prime is at pi, which is cos of pi. Cos of pi is negative 1. We multiply that by negative 1 to get 1. Okay, so the slope there seems to be equal to 1. Okay, so that's our maximum, and that's our minimum, and they occur periodically. Okay, the minimum occurs every 2 pi k. Okay, so it occurs at 0. It occurs at 2 pi. Okay, it occurs at 4 pi, and so on and so forth. Okay, so obviously for all k that belongs to the set of integers, and for maximum they occur at pi plus 2 pi k, where again k belongs to a set of integers. Okay, so the first one here will be pi, the next one will be 3 pi, phi pi, so on and so forth.